So rocks in here are a little bit different than almost everywhere else in Texas, mostly in terms of their age and what type of rock they are. So let's deal with that first. Especially people down here. I'm not up there, it's a little bit harder to see, and I think you're actually standing on something different. But for those of you who are down here, what do you notice, what are the rocks like that you guys are sitting on and looking at? And up there you can sort of look around, try to see what they look like. Is there layering in these rocks, or are they sort of homogeneous? Who thinks layering? Let's raise your hands. Anybody think layering? Anybody see layering? Got a few hands. Put up your hand if you like. Put it up. Go on, thank you. Okay. You see layering, put up your hand. Okay. Up there, anybody see layering? And on top there? Few of you? Okay, good. Alright, so we've got layering. That's good. Looking more closely, can we see the individual minerals? If you get your nose up to the rock, can you actually see the individual minerals that make up these rocks?
I'm not getting my nose.
Just get on your knees and look down.
You can stand in the grass right there and look over.
So can you?
Yeah, you can see it.
Okay, so we can see the minerals. They're visible. What else about the shiny? Okay, that's important. Do they look like sedimentary grains? Are we looking at sedimentary rocks here?
It was metamorph.
Well, yes, because you read the handout.
I didn't. I'm taking the lab.
Okay, so what type of rocks are we standing on here? Igneous, sedimentary, or metamorphic? Who thinks igneous? Everyone raise your hand. Although some of you actually up there are sitting on igneous, so you can raise your hand right now if you want.
Oh, igneous.
Okay, cool. What about you down here? What are you sitting on? Igneous? Who votes igneous? Who votes sedimentary? We're sitting on sandstones. We want one sedimentary down here. Okay. Who thinks metamorphic? Okay, good. All right, we got a bunch of you winning the rock identification prize for the stop. What else about the texture do you notice about these rocks, especially sort of across the lake here on the other side? Are these homogeneous, or do you see banding in those rocks? What do you see? Right. These rocks are pretty well banded. There's compositional variations, right? So what type of rock is this? What's the name that we would use? A gneiss. Right, they're foliated, good. It's a foliation, and these are gneisses. So what we're standing on, for those of you who didn't read the pamphlet, is called the Valley Springs gneiss. And these are actually even older than the Town Mountain granite that we were standing on earlier. These are over 1.1 billion years old. These are probably the oldest rocks that are exposed in Texas. And that's one of the reasons why this region is called the Llano Uplift. It's because you have very old, deep rocks exposed throughout this area, versus the rest of Texas where you have relatively young material at the surface, at least comparatively young relative to this. So we're looking at metamorphic rocks. If you look at the textures at your feet, and for those of you up there, we'll see some nicer examples, or there's another stop here, so don't worry, you'll get to see some nice textures too. You'll see that the fabric is very contorted. It's wiggly, it's been very folded, so there's been a lot of deformation that has affected these rocks during their metamorphism. And if we look across directly here, we can actually see a nice fold preserved in the gneisses on the other side. So I'm going to have to find some rocks for a second, and then we'll point out this structure to you.
Alex.
Are those dice?
I just saw that.
We'll get to that in a minute. You got a good rock?
There's a nice foliated canvas.
Oh yeah. Well,
or do you want something else?
I want a rock.
Oh, a rock.
Directly over there, we've got banding that sort of goes up like this, and then you can see it sort of takes a very sharp hairpin turn, and then over here, it's going down the other way. So if we were to draw this on our whiteboard, the fabric that you can see in the foliation, we've got the layering in these gneisses that goes up, and it turns around and comes down. It goes up, and turns around and comes down. And so, if we were to draw, what type of structure is this again? What is this? What did I draw? A fold, right? It's just a fold. So this would be the fold axis right here. sort of showing which way the two limbs are going. And this is a special type of fold because the two sides of it, the limbs, are essentially parallel to each other. And again, we'll see another example further up, but over there, you can see it nicely. We've got parallel limbs, so we've got what's called an isoclinal fold. So these rocks have been very heavily deformed. So they've been very tightly folded, they've been mashed up and baked and cooked very deeply. So the other thing that we can see over there, go back to Mr. Loudspeaker. Alright, so the other thing we can see across the lake over there where those canoeists are various igneous rocks that are cutting up through the metamorphic rocks. And we can see several different types of relationships. So someone else was asking earlier if they are dikes. They are in fact dikes. So directly across here we can see some really nice examples with these pink bands that cut across the foliation. So we've got a nice cross-cutting relationship, so we know that the granites are younger than the metasedimentary rocks. And then we also know that the granites are younger than the deformation that these metasedimentary rocks experience too, because it cuts across those fold structures. They're discordant to it. So we've got some small dikes, and then we've got this big pink bench across there that sort of comes up again on the other side. It's a great place for jumping off of into the lake. Oftentimes there's people doing that. And that would be more of a sill type structure, so it's sort of sub-horizontal, cutting across the area. So again, we've got multiple generations of igneous activity in here, cutting across these metamorphic foliations. And these are equivalent to the town granite that we just saw. So these igneous rocks are about 1.1 billion years old, give or take. So they're probably not that much younger than the protoliths for the Valley Springs gneiss. Many people interpret the protoliths to be volcanic ash deposits. So this is an area that had active volcanism that was then metamorphosed and injected by plutons. So we're probably looking at a very active tectonic area 1 billion years ago that was causing all of these different events to affect the local area. So we're going to look a little bit more at thinking about what's in these metamorphic rocks.
How deep is the lake? Do you know that?
I don't know. Probably a good 10 or 15 feet in here. All right, so one of the key things about this area is what we can actually see in the metamorphic rocks in terms of the minerals. So if you remember, if you take something like a shale and metamorphose it at increasingly higher conditions, you pick up different key index minerals. So we can think about what the index minerals are in these rocks and how they relate to the tectonic environment. So I'm drawing a graph right now. For those of you who are on the edges, you might want to come around to see it. So we're going to look at depth versus temperature. And there's some really cool minerals called aluminosilicates, Al2SiO5, and they have different forms depending on the pressure temperature conditions. So down here, where things are relatively deep but cool, you get a mineral called kyanite. At relatively shallow conditions, where things are hot but not extremely hot, you get something called andalusite. And then over here, where things are very, very hot, you get a mineral called sillimanite. And so the rocks that we're standing on, and we'll see a nice example again up a little bit further, are just chock full of this other mineral, sillimanite, in places. And we have some other textures that tell us things were very, very hot, but not at too deep conditions within the crust. So if we think about sort of a normal change in temperature with depth or geothermal gradient, usually your average piece of continental crust in a quiet environment is going to have something that looks like this in terms of the increase in temperature with depth, whereas we have a lot of this in here, and so the geothermal gradient was probably a lot more like that. So we have a hot, relatively shallow environment. what sort of tectonic environment would you expect with hot, shallow metamorphism? Where do you get hot? Where do you get a lot of heat and a lot of metamorphism and deformation in terms of tectonic environments?
Some kind of intrusion, like a diverse.
Well, there's usually intrusions associated with it. Yeah, we're thinking more large-scale tectonic environment.
Yeah, so
Contact metamorphism, we're not quite that shallow. We're still deeper than that, but you're sort of getting the right idea. Usually you see this type of metamorphic environment, hot, shallow, associated with volcanic arcs. And so, also associated with volcanic arcs, you get a lot of igneous activity. So we have these intrusions that are punching through the rocks all over the place. And these various pieces of evidence are telling us that we were at a sort of what's called an Andean-style tectonic boundary 1 billion years ago. So we'll just draw a quick tectonic cross-section.
Blends in with the rocks.
Yep.
They're not as funny as UH bullets.
Oh my god, the UV.
So
But I want a different one on camera.
here we are in central Texas 1 billion years ago, and off to our southwest there was a plate, we don't know which one, that was getting subducted underneath southern Texas. So we had a lot of deformation, we were folding the crust, and then associated with that we had igneous activities, so we had these melts coming up, forming plutons, cutting through, and then we were building up a volcanic arc as well. So someone asked if there were volcanoes in Texas. Well, there were volcanoes here. They're just probably about 10 kilometers above where we are now and have subsequently been eroded away. And so again, we were at an active tectonic margin. We were closing up an ocean basin. There was probably some other continent here coming along behind us that docked with North America at that time. And this was during the assembly, this is 1 billion years ago, so this is pre-Pangea. So we were building the earlier supercontinent that we thought think exists called Rodinia. And because of that, we're not really sure what block came in and docked with us. It could have been what is now today part of the Amazon, it could have been Siberia, maybe Antarctica. We really have no idea. But anyway, we know that there was an active plate boundary here because of the rock assemblages that we see. Another key thing to remember is that, again, this was an Andean-type plate boundary. It was like the Andes. So you had a big mountain chain, volcanoes, probably a plateau environment, possibly, and all of that was stripped away over the subsequent 500 million years to form that great unconformity that we just saw at the last stop. So we had a huge mountain range, and then we completely removed it and deposited that hickory sandstone. So again, it took 500 million years, but this is a very dynamic planet. Things change all the time. And Texas was a lot more interesting, geologically speaking, at various times in the past.